Okay, let's get started. We have, I think, some interesting subjects here, actually. And today, I think, quite amazing things go on that are surprising the first time you see them, but afterwards you kind of get the idea. Partly in these wave optics, where we're considering optical phenomena, but we're taking account of the fact that the rays are waves, light waves are waves, and so they do these special things that waves do. I also hope we can move on today to begin on the so-called modern physics, quantum theory. I think I spelled it quantum theory in my notes today, quantum theory, which is a whole new world, begun about 100 years ago. But let's go to the things we should know about in wave optics. Now, basically, there are two main ideas, and if you get that, the rest of them, the rest of the things are just simple applications of those two ideas. The two ideas, I think I said it before last time, are Huygens principle. Well, I think his name is Huygens, so let me put it that way, principle. And then there's the idea of interference. That's something that waves do. Now, the Huygens principle is simply that if one has a wave front, we have something like this going on, we imagine how the wave propagates by saying that every point on the front is a source of new little wavelets. Every point sends out wavelets. And then if we draw the envelope, that is it's really an interference effect. We add up all the wavelets. You see here the wavelet may be going up, and here it may be going, it's going up here, but down there, in between it's going down, and maybe it's going up there. And the net effect is that we get a new wave front due to the interference of these little wavelets. So Huygens principle actually uses the idea of interference of the little wavelets that are coming out. What's nice about the Huygens construction is that it explains why objects don't have sharp shadows. If you look really closely, or you can perhaps remember seeing the edge of some object when a wave comes in. I'm thinking now of a pier. There are poles sticking into the water, and a wave comes in, and you can get waves behind the pole, that are supporting the pier. The wave comes in, but there's waves behind it. There isn't a sharp shadow, as you might expect if there were particles going by. The particles, if it misses, it misses, and if it hits, it bounces back, or it might go that way. But there's nothing behind here, so you're safe hiding from bullets behind something like this, but you're not exactly safe from waves. Because the waves can go, see, by the Huygens construction, the wavelet right here, this part of the wave, sent out, there is nothing to interfere with it behind the thing, so it actually can propagate behind an object. So the Huygens construction gives a model for why waves can appear behind a solid object. So it's a combination of this idea that each point on the wave is a source of a wave, and the idea that those interfere to give you the net wave that you're going to see. So that's really all there is. And what we do in all the examples that we have is we start out with a wave, so we have it nicely as a wavelength, and it's traveling along. But what we do is we break it into at least two pieces. We have the two pieces travel different lengths, different distances, so that they can get out of step. That is to say, if one piece travels a path like this and the other travels a path like this, and they maintain their wavelength, well, they certainly will maintain their frequency. But when they come back together, and then you reunite them at some point, the question is, do they come back in step or out of step? It's sort of like a column of soldiers, and you divide the column into two pieces, and you have everybody marching with the same pace, and then one goes around a corner, around a block, and then when they come back, are they parallel to each other or are they not parallel to each other? That's the issue. That's what we're doing. And we just do it in different fashions. The simplest one is the Young two-slit experiment, where all we're doing is we have an obstacle made into two slits. We send in our wave, like this, and when the wave hits here, the simplest picture is that this wave is now the source of a circular wave going out. Think of it as a point. So it's sending out a wave with the same frequency, same wavelength, so I'll try to make the wavelength the same, sort of coming out like that. Right? Okay, that's it. So we've done this thing where we've got a Huygens construction, the source of a new set of wavelets, and then we separated them into two pieces, and we're going to send them on different paths, say someplace over here, some point P. And this one, its circular wave, will also proceed, and eventually it'll arrive at the point P. The difference being that because this one obviously has traveled a little bit further, so we can draw a perpendicular here. So from here on out, they're the same. The difference is in just this little piece in here. This is the extra path length, because this to that point P at an angle theta, say. Okay? So that's, again, this is the pattern. We take a wave, we break it into two parts, so it keeps its coherence. This wave has the same exact frequency and phase all along here. It goes to the point P. And the question is, how much path difference is at a certain angle? And it depends on the angle, because this angle theta is the same angle theta here. So the path difference, delta L, is equal to, now here's the spacing between these two slits. Let me put it in white, D. The path difference is D, this is a right angle, so it's the sine of the angle theta. So delta L is D sine theta. This is the path difference. And now the question is, if the path difference is such that the waves come in phase, then there'll be a maximum of light. So if the path difference is a whole number of wavelengths, then what's happened is that even though, as long as you haven't exceeded the length of this coherent wave, as I said, the wave from light has a finite length because atoms emit in short of bursts. You excite the atom and it drops down and it emits its light, That's the real physics behind it. So it'll be a finite time and it'll be a finite length. As long as you haven't, say, had one wave and it has a certain length, and then you delay it its twin brother so long that they don't overlap anymore, you wouldn't get interference between those, because if it's delayed so much, it won't overlap with its brother here, twin brother, as it were. So, but as long as the path difference is not that great and the two can overlap, and if you make that path difference equal to a whole number of wavelengths, they will come back in step, because one is advanced a whole number of wavelengths, and so they come back peak to peak, and so you'll get a bright fringe, as we call it. This is for constructive, we also call this constructive interference. Okay? Pretty self-explanatory. Okay, so that's the, or what I illustrate here in this slide is the opposite case, where if that path difference is a whole number of wavelengths plus a half, that half will kill you, because what it does, it means that one of them is a half wavelength ahead of the other, like this, but then its minimum is in step with the other one's maximum. So here's this one is a half wavelength ahead, and then what happens is the crest matches the trough, and you get the destructive interference. So if n plus a half lambda is equal to d sine theta, that is the path difference, then you will get the destructive interference, or cancellation. Or a dark, we also can say a dark fringe. So that's it. That's a simple case. And we apply that. Now here's two slits. The same is true of many slits. The same law holds. The difference is that as you add more and more slits, in addition to these main peaks, well, I didn't say this part. Namely, let's say we talk about constructive ones. You get the constructive interference when n lambda is one wavelength extra length, when delta L is one wavelength, or it could be two. Still the waves, even though they shifted by two, they still come back one upon the other. So you will get a second point, P2 up here, where n lambda, when you have two lambda, is equal to the path difference. Okay? So that we call the second order. And you'll get another bright fringe at when the d sine theta is twice lambda. Because then again, the waves will come in step, crest to crest. Now, as you increase the number of slits, a couple of things happen. One thing is that these peaks tend to get sharper. I think that is shown here where, I don't know how many is written here. But you can see, well, in any case, well, it looks like this may be 3, 4. Can you read that? I can't read off this tiny screen. Is this one 3? Okay, and this one's 4? And 5 maybe? Okay, now, so a couple things you can notice. First, the lines are getting sharper, so the more slits you have, the more well-defined this angle is, because you do have the question of, if you use something like this to measure the wavelength, what you do is you scribe a certain number of lines per inch, so you know the separation. This is done mechanically. It was quite a thing in the late 19th century, describing these lines very, very precisely. They have these called ruling engines, where they draw lines in materials like aluminum and get very precisely, closely spaced lines in order to be able to do spectroscopy. Very important thing at the time, still now. So you want to have many lines, because as you have more lines, these diffraction maxima sharpen up, so you can more precisely get the wavelength, because you see, what is the angle here? This angle, well, if you have a fuzzy thing, the angle is somewhere between here, more or less at the center, but it'd be nicer if it were really sharp. Then you would have very little question of what the angle was that the construction was occurring, constructive interference. Now, the other thing that happens is these little subsidiary maxima in here, and the book doesn't explain quite why there are these subsidiary maxima occur. And it's actually, yes, sir? Yeah, right, it's the number per unit length. Right, we're keeping D constant, I think, in this story. And we're just adding more slits with that same spacing. So you see where the peaks are coming out at the same angle, but they're just sharpening up, and we're getting these subsidiary ones. So where's the subsidiary one? It's very simple, actually. To tell you the truth, I didn't realize this till last night. I was lying in bed thinking about this, and it's really pretty obvious, actually. Because what we have done, you see, what we've counted so far is n lambda. We said that there was an extra length between slit 1 and 2, and let's say 3 and 4. So we have an n lambda, this d sine theta. But there's another n lambda. We can have this one. Namely, from here, well, not to this slit, but how about to this slit? In other words, suppose there was a difference between this one and this one. You see, suppose we had a wavelength between those. Well, the angle would be less, you see, because what we have is 1 extra lambda, but the spacing now is not d, but 2d. So you have 2d sine theta is equal to a whole wavelength. And that's going to give you a sine theta is lambda over 2d in the first order. So what you're going to get, if you get interference between the first and the third slit, you're going to get a peak at, not at theta, but at half of this theta. This will be your subsidiary due to the diffraction between slits 1 and 3. Interesting, isn't it? And so for every slit you have, you'll not only have one between 1 and 2, you'll have an interference between 1 and 3, 1 and 4, 1 and 5, and each one of those will give you a different peak. And so for as many slits as you have, you'll get an additional peak. And that's why, actually, if you count the number of subsidiary maxima here, it'll tell you how many slits you have. It's cute, I think, actually. Get it? Well, think about it. But there's no reason. Oh, and the other thing that's interesting, of course, is that if there's a whole wavelength here, then there's a half wavelength here. So it means that there's a half wavelength difference between this one and this one, so they will cancel. This one will cancel that one, so you're left with only this coming through. So that subsidiary peak is going to be weak because it's only coming from this slit. These other two slits will be destructively interfering. So that also explains why the subsidiaries are weak, because most of it is canceling out. I throw this in as a side. I don't think you have to worry about it. There's a formula for this, but I think there's a simple physical explanation. Yes, Nathan? Yeah, n minus 1 actually. Yeah, depending on how you count them. Yeah, so it's sort of like you get something like this. So you count. This would probably be from like the, and I haven't really thought it out since last night, but one of these is coming from the interference of this 1 to 2, and this is maybe 1 to 3, and this is maybe 1 to 4. So this is the way of sort of counting things. You could check that. Why don't you do? This would be an interesting exercise. I haven't really even done it myself yet, but I think it's a little bit of insight into what's physically going on here. And it explains why there's extra peaks, and it also explains why they're weak. Because for every one that constructively interferes, you'll have some that destructively interfere. It's a very simple model of why there are subsidiaries. Not a big deal, but it's nice to know. In any case, there are these issues of spectroscopy, namely, if you had two spectral lines having different wavelengths, and you have your formula, and lambda is d sine theta. It's a very important formula. If you know d and you measure theta, you can tell what lambda is, and you can measure the spectral lines, which you'll be doing, I think, in your lab next week. So just measure the angle. Somebody tells you what the d spacing is, and you you can figure out the wavelengths. Now, we had this little demo that we did where we looked at a couple of gases that were excited and sending out light, and you could see lines of spectra coming out of them because the different colors, because of their different wavelengths, they will come through at different angles. So you just look at the thing, and you can just, if you measure the angle, and you see it over here, you'll see blue is lambda is smaller. It'll come out. So blue will come out over here, and red will come out over here because the angle of deviation is greater for the longer wavelength. So it's a way of analyzing the colors coming out of materials. A very important thing. It helps us understand atoms. Now, the same trick is done with X-ray diffraction. I showed you this particular demo where we had little BBs, metal balls, arrayed in a square, a layer square like this, and another layer below it, and below it to build up a three-dimensional cubic array of balls. And the radiation came in. So what the construction is here, it's the same idea. Same idea. What we do is we have a beam coming in that's coherent. Maybe over here. We have our crystal, which is made of, in that demo case, balls. It could be a crystal of some material, anything, DNA, whatever you want. And we send in a coherent wave. And the argument is that part of the wave reflects immediately off the surface. The other part, some of it, goes into the material and reflects off these, thinking of these as radiators. They were sort of your Huygens radiators. They were all going to send out their waves. And this one's going to send out its waves. But this one has a longer path length because it's traveled into the material. And the longer path length is, if here was a wavefront, we would have a wave that came into here. Up till here, they're the same. So the extra path length is this distance plus this distance. So we're doing the same trick. We have a wave coming in. We split it. One of them travels an extra amount. This is an L, and here's another L. So you have 2L is the extra path length in this case. And if this is the angle theta, this is also the angle theta. Oh, by the way, it turns out in crystallography, they choose the angle with respect to the planes here rather than with respect to the normal. It's just a historical convention. I think it was Bragg, who did a lot of the early X-ray work. He happened to choose the angle this way, whereas we're accustomed to doing with respect to the normal. But the convention in this crystallography field is to take it with respect to the surface. Be that as it may, there's an angle theta in here, so that this extra length, if this is the distance between the planes, which is what we're trying to get at, this is a crystalline spacing, the extra distance is d sine theta again. 2L, well, one of the L's, so it's, one of the L's is d sine theta. Right? So 2L is 2d sine theta. And to get a maximum, you want that path length to be a whole number of wavelengths. Right? So that this one travels a whole, this plus this has to be a whole number of wavelengths. Where here on out they're the same, and when they recombine, they are a constructive interference. So here you would get constructive interference, which we did. As you recall, I was able to move the detector around in a certain place, certain angles, we pick up a maximum. And so this is the Bragg law, and lambda is 2d sine theta. And so if you know the wavelength of the radiation you're sending in, and you know which order it is, how many wavelengths you got, you can just keep going until you find the shortest path. It'll be the sort, like angle of MD1 is 2d sine theta. You measure theta, it tells you the spacing between the atoms in the crystal, which is a very big deal. But again, let me emphasize, it's the same story. We take a wave, we split it in two parts, we send them one part along the different paths, we recombine them, and if they come out in step, we get a bright fringe, large intensity. If they come in half wavelength out of step, you get a null, and it tells you something. Same story. The same story goes on with a thin film. The idea here, same story. I hope this guy here does, but maybe I shouldn't go into it too much detail because time is flying. But the idea again is you send in light into a material like a thin film. Sometimes you see oil slicks on the ground or water films, and part of it reflects off here, part of it travels through,